So in this example, use the nodal analysis to find a VO in the network. VO is over here. By looking at the problem, we notice that this problem has a voltage source. It also has a dependent current source. So for a circuit problem with the dependent current sources, we need to treat that source as an independent source from the beginning. In addition to that, we find another equation that is about this controlling variable. The controlling variable in this problem is a VO. Nice, that's something we are looking for. Step 1, I'm going to select a reference node and label all the nodal voltages. VO is compared between this node and this node. And at the same time, this node connects to multiple branches. So we want to make it a common reference. Select this node as my reference node. Then what are the nodal voltages? This node have a nodal voltage of VO.
Professor, I have a question.
Go ahead.
Why did you choose the node where you chose it instead of in the middle? Or like why not the middle? I understood why not the right last one, but why not the middle?
This is a one node. Although it's labeled as a dot in the circuit diagram, but this is one node. There is no element between these two dots. This is simply just a wire. This is one node, so it doesn't matter where I put it. I can put it there as well. It's the same.
It's considered a supernode, correct? That's why we could consider all three of those dots the same node.
So this one is not a supernode because this is this is just one node. So you brought out the concept of supernode. Sometimes we treat part of a circuit as a one node. In that case, we call it a supernode. For example, like I can say this all together. I treat all this together as one node, and the current goes into this node should be equal to the current leaving the node. So in this case, this part of the circuit, we call it a supernode. What we are dealing with right now, it is a one node. Let's label the other nodes as well. This node will be, let's call it V1. And there's another node over there. Let's call that node V2. And we know that we want to maximize what's given in the problem. We know this node is higher than V1 by 12 volts. So we just call that node V1 plus 12. So this node has a nodal voltage of V1 plus 12. So we maximize the utilization of all the given information from the problem. That will help us limit the number of unknowns. So eventually you will come with an equation set that is easier to solve. All right, I think we labeled everything. And on top of that, we also know the relationship between VO and V1 plus 12, right? Because this is two resistors in series, and by using the voltage division, we'll be able to find the relationship between VO and V1 plus 12. Let's see which node we're going to pick to write a nodal equation. What do you think?
We can't use V1 and V1 plus 12, right? Because of voltage there.
That's a good catch. So we cannot do it here. We cannot do it here. And if we do it here, we get a very limited information because we already know the relationship between VO and V1 plus 12 by using the voltage division. So there's only one
reference,
left.
Right?
Yeah, perfect. Yeah. So we're going to write a nodal equation about the reference point. We can count the current leaving the node as up to 0. So let's do that one by one. So let's do it from here. The first branch, that is VO over 2. So over here, I'm going to select a kilo ohm and a volt at the unit, then the current will be milliamp. If we do this, and we don't need to worry about the K. The reason that we put a 2K over here just to make it a standard unit. I'm going to use a kilo ohm, volt, and a milliamp as my unit. So when I write the equation, it becomes a little bit simpler, so I don't need to carry the K all over the places. Current leaving this node in this branch, that is a VO over 2. So the second branch, the current leaving this node, should be 0 minus V1 divided by 1. So we'll put a negative on the top. The current leaving in this branch, that is what? That is a 0 minus V1 plus 12 divided by 1. The current leaving this branch, that is a 0 minus V0 divided by 1. So now we get all these 4 branches, 1, 2, 3, 4. We get all these 4 different branches, so this should be equal to 0. So that is the first equation. There will be another equation about the control variable. The controlling variable is VO. So we're going to find a VO in terms of the other nodal voltages that we defined in the problem. So we only define a V1 and a VO. We define a relationship between VO and a V1. So we know that this is a voltage division circuit. So this is a 1 ohm, 1 kilo ohm. We know that VO is half of that, which is very nice. So which is V1 plus 12 divided by 2. So that is how we find the second equation. Now we have all the equations we needed. Step 4, we're going to solve the equations. So we simplify them one by one. I will multiply by 2 on both sides. So I have a 1 VO. This is minus 2 VO. So that is so minus VO. And we have minus 2 V1 minus 2 V1. So that is a minus 4 V1. And on top of that, we have a minus 24 that is equal to 0. So we put it on the right hand side, that becomes 24. And if you don't really like the negative sign, you change that sign, then you put a negative sign on the right. This is how we simplify the first equation. The second equation, we have a V1 that is equal to 2VO minus 24. So then we find a V1 that is 8 over 3 volts. Then we can find a VO. VO is a V1 plus 12 divided by 2. That is 22 over 3. The last step is to write the conclusion. VO is equal to 22 over 3 volts. So this is how we solve this problem. So here we have 4 additional practice problems. The first problem, 3.9, find a VO in the network. So VO is over here. And we have current sources. You know that we can model by inspection. So model by inspection. So we'll still need to go through the same process. The first step, we're going to select a reference node and label nodal voltages. So which node are you going to select? It looks like a VO is something over here. If I select this node as reference node, then I will have one node have a nodal voltage of VO. So that's probably something I'm going to do. So I select this node as reference node. Then I'll label all the other nodes. So this node will be VO. This node I don't know. This node I also don't know. So I'm gonna put those there as well. So I'm gonna call this node a V1. I'm gonna call the other node a V2. There is another one here. Call this one V3. Now I labeled everything. So if I do a model by inspection, I can write the equation about everything in this problem. So let's try that. So I have 4 different unknowns that is equal to something that's given in the problem. And this matrix should be a 4 by 4 matrix. Should be something like this eventually. Let's put the unknown there first. So I'm going to put a VO, and the next one is a V1, put a V2, and a V3. And on the right hand side will be the current goes into the node. For this node VO, there is a one current source that is leaving.
Negative 2.
So we have a negative 2 over there. Good job. So for V1, and there's a 1 milliamp that goes in, so that is 1, right? And for node V2, there are 2 current sources connected there, and both of them go in there. So that's a 2 plus 4, and it's 6. And the last one, V3, there's a 1 current that is leaving, so we have a negative 4. So that's how we get the right hand side. This matrix is tricky, so that's where we spend the majority of our time on. We'll start with diagonal entities. The diagonal entities are the conductance connected with these nodes. VO, it has these 2 resistors directly connected to that, so we will need to use the conductance of this resistor plus the conductance of that resistor. So that is 1 over 1 plus 1 over 2. And for the second node, V1, we have 3 resistors connected to that. So that is 1 over 1 plus 1 over 1 plus 1 over 2. For element 3, for V2, there is only 1 resistor connected to that, so which is nice, so which is 1 over 2. And for the last node, V3, there are 2 resistors, 2 branches with a resistor connected to that, so that is 1 over 1 plus 1 over 1. Now we get all these diagonal entities. The rest will be the shared resistors between different nodes. So this is the first row, second column, so it's shared between VO and V1. Between VO and V1 there is a 1 branch shared, so that is a -1. So this one is the first row, third column. This is between VO and V2. VO and V2, nothing there. So this is why we have 0 here. And this one is between VO and V3. VO and V3, there's no direct branch connected between the two. So that is 0. We also know that this matrix is symmetric. This is a -1 over 1, and this will be 0, and this is 0. This entity over here, that is determined by the shared branch between node 2 and 3, because it's the second row, third column between node 2 and node 3, so that is V1 and V2. Between V1 and V2, there is a 1 shared resistor, which is 2, so which is why we have a -1 over 2. So over here, this is between node 2 and the last node 4. So between 2 and 4, which is V1 and V3. Between V1 and V3, there is a 1 shared resistor, which is 1. So this is why we have a -1 over 1. Still, we have a negative sign. Since this matrix is symmetric, and we know here is a -1 over 2, and this is a -1 over 1. This is a third row, last column between V2 and V3. Between V2 and V3, there's no shared branches with the resistor, so that is 0. This matrix is symmetric, this is also 0. So this is how you set up the equation. After you set up the equation, you can use the inverse of that matrix times this to help you to find a VO, V1, V2, V3. So let's just simplify it a little bit. This will be 1 plus 0.5, 1.5. This is a -1. This will be a 2.5. This is 0.5. And this is 2. And this is -0.5, -1. And this matrix is symmetric, so we already know that. So it's a -1. It's a -0.5. And this is a -1. So it looks a little bit better now, right? VO is equal to 1.6 volts. V1 is equal to 4.4, and V2 is equal to 16.4, and V3 is equal to 0.2. So this is the way how we solve this problem by using model by inspection. If we do it in a general method, so the second step is to write the nodal equations. To write the nodal equations, we need to look at this node at least, right? So if we write the nodal equation about this node V0, we'll count the current leaving V0 as a positive. So the current leaving V0 in the first branch, that is a VO minus V1 divided by 1. The current leaving in this branch, which is a VO divided by 2. And the current leaving this node from this branch, that is 2. Plus 2, that is equal to 0. So this is how we get the first equation. The second equation about node V1. The current leaving V1 from this branch, the top branch over here, that is V1 minus V2 divided by 2. The current leaving V1 from this branch, that is V1 minus V3 divided by 1. And the current leaving V1 from this branch, that is V1 minus VO divided by 1. The current leaving this node V1 from this branch, that is a -1. So that is how we get the second equation. continue to write a nodal equation about a node V2. So look at the node V2 over here. Count all the current leaving the node as up to 0. The current leaving this node from this branch, that is V2 minus V1 divided by 2. And the current leaving this node from this branch is -2, from that branch -4. That is equal to 0. So this is how we get the third equation. The last equation is about a node V3. The current leaving this node from this branch, that is V3 minus V1 divided by 1. The current leaving in this branch, that is V3 divided by 1. The current leaving this node from that branch is a 4. That is equal to 0. So this is how we get the 4 equations. So after you get all these 4 equations, step 3, you can solve these 4 equations. If we do everything right, we should be able to find a VO of the same answer. Alright, let's look at the next question. So step 1, select reference node and label nodal voltages. Which node are you going to select a reference node? So when finding V0, VO is over here. So it looks like I'm going to select this node as reference node. These two are the same node, so it doesn't matter where you put it. Let's label the nodal voltages. So we have VO as one node, which is over here. In addition to that, if I select this node as reference node, this node will have a nodal voltage of 12, right? And this node, I don't know, so I'm going to label it as V1. So in this problem, we only have 2 unknowns. So the second step is to write the nodal equations. By looking at a VO, there are 3 branches connected to that. The current leaving VO from this branch, that is VO minus 0 divided by 2. The current leaving in this branch, that is -2. The current leaving in this branch, that is VO minus 12 divided by 1. So we get all the 3 branches, that is equal to 0. So the next equation is about this node V1. The current leaving this node from this branch, that is V1 divided by 1. The current leaving in this branch is V1 minus 12 divided by 2. And the current leaving in this node from this branch, that is positive 2. So that is equal to 0. Now we get everything. So step 3 is to solve the equations. So we simplify the 2 equations. For the first equation, I will multiply 2 on both sides. So I have a 3VO minus 4 minus 12. So that is minus 16. That is equal to 0. And you notice that if we are looking for VO from this problem, and I can solve it already directly from here, I don't really need a second equation to find a VO from this problem. So which is nice. So if you can notice that, you can give the conclusion directly, because I already solved VO from there. VO is equal to 16 over 3. So step 4 is to write the conclusion, say VO is equal to 16 over 3 volts. Next problem. In this example, we're going to find a VO in the network using nodal analysis. VO is over here. And this problem is different from all the other previous problems because this one have a dependent source. So that is the only difference. So we're going to do the same thing in the first step. Select a reference node and label the nodal voltages. Since we are looking for a VO, I'm going to select this node as my reference node. Label the nodal voltages. I have a VO here. And this one, I'm going to make use of what's given in the problem, so that it's 2VO. So this node have a nodal voltage of 2VO. And this node is not labeled yet, so we're going to label that as V1. Now I labeled everything. So the next step is to write a nodal equations. Which node are we going to pick to write the nodal equations? We're looking for VO. At least you need to find one related to
V1.
VO, right? So we'll start from here. The current leaving from this branch, that is a VO minus V1 divided by 2. Current leaving from this branch, that is VO minus 2VO divided by 1. So we get everything, right? So that is equal to 0. So looks like we have another variable V1 over there. So very likely that we need another equation about this node V1. So at this node V1, we write the nodal equation. It has 3 branches. The current leaving from this branch, that is V1 minus VO divided by 2. And the current leaving from here to this branch is V1 minus 2VO divided by 2. The current leaving from this branch that is negative 2. So now we get all 3 branches that is equal to 0. And on top of that, because we have a dependent variable, this dependent variable depends on VO. Since VO is already written in terms of the variable that we have, because we define VO as a nodal voltage already, so the additional controlling variable is basically telling us VO is equal to VO. So it doesn't bring any new information. So we don't need to write the last equation. Then we can solve the equations. Simplify the first equation. V1 is equal to VO. From the second equation, what do we have? Do the same thing. We multiply the equation by 2 on both ends. So this is V1, 2V1 minus 3VO is equal to 4. 2V1 minus 3VO, that is equal to 4. Then we can find a VO and a V1. So VO and that is equal to V1, that is equal to negative 4. So step 4, that is the conclusion. So this problem asks for VO, so we just tell you the VO is equal to negative 4 volts. Alright, any questions? The last example, determine VO in the network using nodal analysis. So VO is over here. Has a lot of loops or meshes in the circuit. It also have a controlling variable, which is Ix. So we need to use a general method. So we're going to follow the step how we solve problems in general to work on this problem. Select reference node. Since I'm looking for VO, maybe I will select it from here. If I select from here, I will have a nodal voltage defined, which is VO. So label the nodal voltage is VO. How about the other nodes? And this node have a nodal voltage of negative 12 because this node is lower than the reference node. We can continue and label the other nodal voltages. So this one we don't know yet, so we will call this one V1. And on the top there is another node up there, so we'll call that node V2. Now we labeled everything. The second step is to write out the nodal equations. Step 2, write the nodal equations. So we'll start from node VO. So nodal VO have 3 branches connected to VO. So the current leaving this node from this branch, that is a VO divided by 1. The current leaving in this branch, that is a VO minus negative 12 divided by 1. So this is VO minus negative 12, so that is a plus 12, right? Divided by 1. The current leaving from this branch, that is a negative 2, that will give us 0. So this is nodal equation about node VO. So the nodal equation about node V1 is over here. There are 3 branches connected to V1, so we'll do it one by one. And the current leaving from this node through this branch, that is V1 divided by 1. The current from this branch, that is V1 plus 12 divided by 1. And the current in this leaving from this branch, that is negative 2 Ix. That is equal to 0. So this is how we get the equation about this node. The next node is about this node V2. Again, 3 branches. The current leaving from this branch, that is V2 minus negative 12 divided by 1. The current leaving from this branch, that is 2. The current leaving from this branch, that is 2 times Ix. So now we get the 3 nodal equations. And remember, there is a controlling variable Ix. So it means that we need an additional equation, which is about this Ix. This is called the addition about this controlling variable. So we're going to write Ix in terms of the nodal voltages that we defined. So let's see. Ix is over here. I can write Ix by using Ohm's law. That will give us the expression by using nodal voltage VO. So that is Ix, that is equal to this negative 12 minus VO divided by 1. So that is the last equation. So now we have 4 equations to solve. So step 4, solve the equations. So we'll simplify it a little bit and see what we have. So the first equation tells us that 2VO plus 10, that is equal to 0. So we can find a VO that is equal to negative 5. We find a solution from the first equation. This problem looks complicated, but it's actually pretty straightforward to solve. Step 5, we'll draw the conclusion.